Welcome back to Physics with Miss McQueary, everybody. And today's lesson is going to be on vectors. And I would be absolutely remiss if I did not include a little bit of despicable me humor here with our good friend Vector, because he commits crimes with direction and magnitude. Oh, yeah. And you're probably going to get sick of Vector after seeing this PowerPoint. But that's okay. That's by design. I want you, whenever you think of vectors, think of this guy. All right, we'll explain why here pretty soon. There are two things we're going to be talking about today. Number one, what's a scalar? What's a vector? What's the difference? Number two, adding vectors in one dimension. Well, if we're going to be able to distinguish between scalars and vectors, we got to know what each one of them is. A scalar is basically anything in physics that has magnitude but not direction. What is magnitude? This is probably the first time you've heard of it, right? Magnitude is basically how big something is, how much of it you have, all right? It can be, an example could be basically anything we measure. It could be the length of something. It could be, in this case, the mass, age, heat, temperature. It could be anything like that, right? All those have a definite magnitude associated with them, all right? None of them have a direction. You don't say that you have a direction for mass or your distance is going somewhere, right? You'd be very careful about that one. There's no direction with your age or with things like heat. All of four of these examples have to do with the Triceratops, actually. The mass, the distance, basically the length, how long ago it lived, and its approximate caloric intake each day are all based on a Triceratops. And none of them have direction, right? They all have magnitude. They all have how much of it they have. They just don't have a direction at all. So far, so good? All right. Now, let's compare that with vector. All right. And this is where vector from Despicable Me comes in. Vectors is any direction or any quantity that has both magnitude and direction. Oh, yeah. Now, when we talk about magnitude, we said how much that we have. And then a direction is what it sounds like. Where are we going? Now, you need to have at least one direction for your vector. Not that direction, not one direction. We mean like north, south, east, west, counterclockwise, clockwise, up, down, maybe left or right, or maybe towards something or away from something. Those are all examples of directions we can use to describe our vectors in physics. Examples include velocity, acceleration, and force. Notice each one of them has a direction tacked onto the end there. North, east, left in this case. Now, one of the things to be really careful with is how we represent these vectors. A scalar would just have, in this case, an A. A vector has this little half arrow above it. It's like someone forgot to draw the rest of the arrow. That's to tell us that it's a vector we're dealing with. It's got direction and magnitude. We need to know that. Sometimes in your textbooks, you'll see a bold A, all right? But on your paper, it's really hard to write in bold. So put a little half arrow above it to let us know that we're dealing with a vector. Let's play a little game here. Scalar or vector. 27.8 miles per hour, the fastest speed that Usain Bolt has accomplished. Does it have a direction? No. So it's a scalar. 660 million miles per hour clockwise. The speed, or I should say velocity, that Superman travels to save Lois Lane, the 1978 Superman film. There's a direction, right? Direction, a magnitude. Oh, yeah. It must be a vector. About 20 paces northeast. Like if the Goonies are looking at a treasure map, they might find one of those as the steps on there. It's got direction and magnitude. Oh, yeah. Must be a vector. And then last, 110 feet, the length of a great blue whale. There's no direction, right? Got to be a scalar. All right. So that's the difference between a scalar and a vector right there. Basically, it doesn't have direction. We can describe these vectors a couple of different ways. For example, we could look at the green arrow here, which is a vector, and we could say that that is 4 meters to the right. We describe that vector. We can also describe this blue vector. We start at 9. It looks like it goes 6 to the left, 6 meters to the left. Those are how you describe both of those vectors. You can also describe them in terms of vertical vectors, right? Not just left and right, but also up and down. So you could say, for example, the green arrow is 5 meters down, and the blue arrow is 2 meters up. That's how you would describe those vectors. Sometimes we're given specific directions like north, south, east, and west in our problems, or maybe towards an object or away from one. If you don't have those, you can always fall back on up, down, left, and right. Nope, there's Vector. He's back again. Now, how do we apply these vectors? Well, if we have two vectors that are going in the same direction, we can add them. Let's start with a picture. If a man walks 54.5 meters east, what does that look like? Looks just like that, right? And then if he goes another 30 meters east, what will that look like? If we calculate his displacement to where he started, we would say he traveled 54.5 meters plus 30 meters, which is 84.5 meters to the east. So we notice we added those two vectors. Our sum, or our resultant, it's a new term we're going to hear about, which is basically the sum of your vectors, is also a vector. Be very careful on that. All right. What about another one? This time the two vectors are going in opposite directions. Let's draw that picture again. The man still walks 54.5 meters east, but this time he goes 30 meters to the west. So he's backtracking. Now, what's his displacement? This time, since they're going in two different directions, we're going to subtract. So in this case, he only actually went 24.5 meters to the east. Once again, our resultant is a vector. Last part is multiplying our vectors by constants. You can stretch and shrink vectors based on the constant you put in front of the vector. Let's take vector u, for example. Vector u can be squished together like the accordion that this cat is playing if you put a number in front of it that's less than a 1. Also, it can be stretched like parts of the accordion when you put a number in front of it, a constant in front of it, that's greater than 1. Let's see what I mean here. Here's vector u again. We put a 2 in front of it, the magnitude of the vector will double. Notice it's still going in the same direction. Direction does not change when you multiply by a positive constant. You could put, instead of 2 in front of that vector u, you can multiply by 1/3. In this case, it's still the same direction, but it's much smaller. Your girlfriend the cat again, right? So 1/3 is when we squeeze them together, and then the 2 was when we were pointed apart. Another example might be if you put a negative in front of it. This time something weird happens. You're going to take the direction of u, and you're not going to change the magnitude, right? Because it's kind of like there's a 1 in front of it. It's like it's a -1 times u, right? So the magnitude won't change, but the direction will. It will change direction to go opposite the way it was originally traveling. You can combine the two. You can have a negative and a constant in front of it, like -1/2 u. In this case, you have to do both things. You have to, 1, change the direction of the vector, and 2, you're going to change the magnitude of it by making it half of the length, like this. Our true learning targets today have both been met. We know what a scalar and a vector is. We know the difference between them is direction. We can also add vectors in one direction. When they're in the same direction, we will add them. If they're in opposite directions, we will subtract them, and then keep the direction of the largest original vector. Until next time, see ya.